Good day, and welcome to CFE Media's Virtual Training Week. For this session on using wireless sensors and real-time data to improve maintenance practices, we'll be joined by Brad Hopkins, Director of Condition Monitoring, Product Management in IoT Services at HID Global. I'm Kevin Parker, an editor with CFE Media and Technology. Following the presentation, be sure and stay tuned for the live Q&A. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Discover the latest technology in plant maintenance practices and how to apply this to your facility. Keeping manufacturing machining running is critical to plant operations, but how to do that is changing with new technology. Be ahead of your competitors with knowledge-based measurements. Learn innovative ways to keep your operations functioning at peak performance. Attendees will learn how wireless sensors make it possible to track equipment remotely, how advanced analytic techniques using vibration metrics are having impact on industry, and finally, edge processing versus cloud computing and your IoT strategy. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left-hand side of the screen. If you'd like to take notes within the session, click on the left panel to do so. Please remember that this session will be made live on April 1st at 2 p.m. Central, 3 p.m. Eastern. The question and answer session with our industry expert will start approximately at 2:45 Central, 3:45 Eastern, or immediately after the presentation ends if it goes long. Answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left-hand side of the screen. Zoom invite details can be found in the Additional Resources tab under Q&A session. Want to take the session again? No problem. This session will be available on demand. If you're experiencing difficulties, please log out and back into the session to continue. Attendees are eligible for one PDH credit for this event airing on April 1st, 2021, and is categorized within the technical health and safety, including core technical category for RECEP. Before turning to our presentation, we'd like to share a brief video from today's sponsor.
You already know that real-time predictive maintenance is the best way to monitor the health of industrial equipment and prevent unplanned downtime, but that can be expensive. Did you know that with HID condition monitoring, you can afford to monitor all essential systems in the manufacturing process? Don't stop at just expensive equipment. Protect your entire workflow with HID beacons on every machine, all with easy deployment, real-time analytics, and machine learning. See how your business can avoid costly failures with HID condition monitoring. Because isn't every asset in your business mission critical?
I'd now like to introduce today's speaker. Brad Hopkins is the Director of Condition Monitoring Product Management in IoT Services at HID Global. He received his bachelor's, master's, and doctorate in mechanical engineering from Virginia Tech in 2008, 2009, and 2012, respectively. Previous positions include Condition Monitoring Project Engineer and Senior Data Scientist at Amstead Rail Company, Inc., as well as adjunct faculty in the Mechanical Engineering Department at Southern Illinois University. Brad, welcome to today's Virtual Training Week session, and please go ahead.
Thanks, Kevin. So I'm going to now cover session 3, using wireless sensors and real-time data to improve maintenance practices. If you've attended the other sessions, you know that session 1 we covered enabling predictive maintenance using condition monitoring. So we talked about how various condition monitoring solutions are the enabling factor in implementing predictive maintenance. And then last session, we did a deep dive into the fundamentals of vibration-based condition monitoring, got into some of the baseline physics to understand how that actually relates to sensors and how we can actually use that practically in assessing condition monitoring solutions. And now we're going to get a little bit more practical in this third session, and we're going to talk about some specifics of wireless sensors and actually using real-time data to improve our maintenance practices. Just a quick review from last time, we talked about how there are two primary types of accelerometers that can be used in terms of technology. The first one is piezoelectric. These are typically more expensive, on the order of thousands, possibly tens of thousands of dollars in some instances. However, very high quality, very high bandwidth data, also require substantially higher power than other technologies. Very low noise though, which means it's a high quality signal. So depending on the use case, this may be what is needed. We also talked about how more recently there has been an emergence in MEMS accelerometers because they are relatively inexpensive and low power, medium to high noise, but high value for the cost. We also talked about how accelerometers have a characteristic called bandwidth, which is essentially the range of frequencies that they are able to detect. And we talked about how it's important to understand the bandwidth of the accelerometer or the condition monitoring hardware that we're using and setting the right expectations for the different types of defects that it could potentially detect. We also talked about how piezoelectric accelerometers in general do have much higher bandwidth, but come also at a much higher price point. And with some of this MEMS technology, we're actually getting a really good trade-off between value and cost. Then we also talked about some basic techniques that we could use. We talked about how we can actually get a velocity signal and some time domain metrics that we can calculate, specifically root mean square or RMS, looking at the energy in the signal and how that changes over time, and how there has been quite a bit of research done in this area over the last several decades, lots of published standards. So this is oftentimes a really good starting point. But we want to use this as a springboard now in this session to talk about other techniques that we can use and how we can actually implement this into the maintenance workflow. So now we're going to jump into wireless sensors and using those wireless sensors to collect real-time data and improve maintenance practices. So we talked about in session one some of the components of a condition monitoring system, but now we're going to look at it more from a wireless condition monitoring system perspective. So we said that the primary sensing element is the accelerometer, typically measuring acceleration or vibration in 3 different directions. Also very common is a temperature sensor, which can be used to measure the temperature of the asset or the environment in which the asset is located. And then the device itself is typically going to have several microprocessors on board to collect data, to manage the sensors, to do processing of that data. And we also talked before a little bit about edge processing and how we can do calculations on the sensor, on the device before we send it to the cloud. And that is a big enabler of some things that we can do with wireless technology. Oftentimes there will be additional memory for temporary data storage or data logging, and then the RF radio, which truly makes this wireless technology. In the conversation that we're going to have in this session, we're going to talk specifically about Bluetooth chipsets, because this is the Bluetooth protocol has been used in quite a few condition monitoring solutions in recent years and has been a big enabler of low-cost deployments of condition monitoring solutions. And then for a system like this, we would also see a battery in it, which is going to power all of the electronics on a single charge, typically on the order of several years. So when we're looking at a wireless platform, there are primarily three components. There is the sensor itself, which is going to be installed on the asset to be monitored. And then that sensor is going to transmit data over some sort of radio protocol. In this case, we're going to use the example of Bluetooth. So Bluetooth itself, as you have probably worked with it and used it in maybe home applications or personal use, maybe you've paired wireless headphones to your mobile device, or maybe you've paired your mobile device to the sound system in your vehicle. But as you know, when you're doing that, you walk through the process of pairing two devices together so that they have a dedicated connection. And as you probably also know, when you have that dedicated pairing and you use it for long periods of time, it drains batteries very quickly. This is why there was a portion of the Bluetooth protocol developed called low energy, in which we changed the way that the devices communicate. So in the low energy protocol, rather than having a permanent dedicated connection between two devices, we use what are called low energy advertisements. And using this approach, the sensor is essentially able to blink data advertisements constantly at very, very low energy. And then a gateway in the vicinity of the device is able to see those sensors, is able to see the data from multiple sensors, pick it up, aggregate it, and then send it on to the cloud, maybe over Wi-Fi, maybe over Ethernet. And then that data can be further processed in the cloud to do more advanced analytics. The cloud also typically, in most cases, is going to be storing the data. It's going to be sorting out redundant data. It's going to be managing it, making sure that it's secure, and then also performing all sorts of analytics, which we're going to jump into some of that a little bit later. But it'll be performing analytics, sending alerts. Typically also there's some type of user interface where the end user can interact with the system, retrieve data, visualize alerts, etc. So I want to revisit the conversation on the accelerometer and how it's used, because that's important to understand how it can improve maintenance decisions, because there are a lot of different ways that we can use vibration data. So typically in a wireless condition monitoring system, you're going to have the accelerometer measuring vibration in three different directions, which is going to capture all of those primary components. But it's collected in different ways and it's processed in different ways. So we talked about edge process data. And again, in IoT jargon, edge means that the processing is done on the edge device, or the device that is connected to the asset to be monitored. And this is opposed to cloud processing, where we are processing data at a different location, typically on a server that is offsite. And we're leveraging both edge processing and cloud processing in our approach. But before the data leaves the device, we are doing some level of edge processing to it. So we talked about using various metrics related to machine health, like peak to peak and RMS for velocity and acceleration signals. A key thing here, though, is by taking this approach of processing data on the device and calculating metrics that are related to machine health on the device, we are substantially reducing the amount of data that actually needs to be sent to the cloud. And what this really helps with is prolonging that battery life for wireless hardware. So when we're looking at solutions that should be lasting several years on a single battery charge, we can achieve this by doing edge processing and then leveraging that low energy protocol. The only downside is that it may be limited in its use, Because as we talked about in session 2, while the edge processed metrics are very useful in maybe fault detection or doing a quick scan or spot check of a machine, they are limited in that it's not giving us that deep dive into the frequency content. So that's when we would jump into the next use, which is getting raw or unprocessed data off the device. And rather than doing calculations on that data, we're sending full bandwidth, full sampling rate data off the device so that we can do further processing somewhere else, like in the cloud. So this is going to be much higher bandwidth. It oftentimes will require some level of expertise to interpret or some sort of advanced software package or third-party tools. And because this data is collected at a very high rate, it will oftentimes take a big hit on the battery. So we don't want to be collecting this continuously. It's typically only done intermittently or on an as-needed basis. So back to the edge processing to review some of the metrics that we could be calculating. If we have a raw signal, we could look at different metrics like taking the max value, which is just the peak. We could look at the max minus the min, and we would call that peak to peak, or we could calculate root mean square, RMS, and this is giving us sort of an average energy that's in the waveform. And what this looks like on the device, so in real time, what we can do is we can collect data on the device at a very high sampling rate. And remember, when we talked about in session 2, we want to use a very high sampling rate so that we can use the full bandwidth of the part of the condition monitoring solution. And by increasing the bandwidth of the condition monitoring solution, we can increase the range of defects that we're able to detect. So by collecting data at a very high sampling rate, very high bandwidth before we process it, we're catching a lot more frequency content. But then at the same time, by performing these edge calculations, we can substantially reduce the amount of data that we have to send to the cloud. So if you think of an example in which we collect data on 3 axes, the X, Y, and Z axes, and for example, we do this for 4 seconds on each axis at a high sampling rate of 25.6 kilohertz. If you calculated that, that would be over 300,000 data points that are being leveraged over the course of 4 seconds. So this is a lot of data, and it would be a pretty big hit on battery life to try to send all of this data to the cloud, to stream it all to the cloud, and to do this consistently. But of course, what we can do is we can take this data on the device, do some edge calculations, and calculate peak to peak, RMS, et cetera, on each of the axes. And then what we can also do is take the same raw data and run it through digital filters. So we talked in session 2 about different types of digital filters like high pass, low pass, et cetera. We can use some clever implementations of digital filters to transform the acceleration signal into a velocity signal and perform those same calculations. So what we've effectively done is taken over 300,000 data points and transformed it into just 18 data points that are representative of the machine health, and just sending those to the cloud. And by doing this, we can perform this cycle once every couple of minutes and send new data to the cloud every couple of minutes, rather than having to wait, once a day or once a week or once every several weeks with the higher bandwidth data. It's important to keep in mind, though, that while I'm explaining all of these mechanics of signal processing to you, typically as a user of the system, you're not going to have to worry about any of this. This is just a peek under the hood as to what's going on. And out of the box, typically condition monitoring solutions are going to perform something like this on their own in standard operation. And then I also talked about how those edge metrics, they're getting advertised over the low energy protocol once every couple of minutes. So the data is being processed on the device. But then the question is, we advertise that data, the cloud is seeing new data once every couple of minutes. How do we take that data and do something meaningful with it? So even though we've already done a lot of processing of the data on the device, we want to do further processing in the cloud to understand what is actually going on with machine health. So let's talk about a couple of different approaches that could be used in cloud analytics. So simple processing, we can revisit our velocity RMS chart, where we're just taking those velocity RMS values and comparing them to thresholds. And we can set different thresholds for different machine sizes or different classes, and then various threshold levels that would indicate some severity. You see A, B, C, D going up in severity, and we can apply those thresholds and just simply monitor that data over time. And when a threshold is crossed, we can send an alert. So this is a good quick approach because it's fast, it's straightforward, and it's a good initial screening. It's sort of like going to the doctor's office and getting your temperature taken. If your temperature is above a certain level or substantially above a certain level, it can be an indicator that more tests need to be done. But if your temperature is normal, oftentimes it's an indicator that you're probably okay. It's not a sure-proof method, but what it does is it gives a good initial screening and oftentimes helps you understand if you need to take a deeper dive to look at something a little bit more. We can also do something a little bit more advanced, still trying to take this fault detection approach, but instead of just looking at a simple threshold, we can do something a little bit more adaptive, like machine learning. So we can use machine learning, and it will oftentimes take some time to build a model, but depending on what solutions you implement or adopt, they will typically do this automatically for you. And the good thing is that these approaches, if implemented correctly, can be much more adaptive. So remember in session 2, we talked about how every machine that you install on, it's going to have that different transmission path. So everything that's measured, everything is going to look very different depending on what machine you install it on or where your mounting location is. And sometimes a simple velocity RMS threshold approach isn't going to give you the best fault detection performance. So we can leverage more advanced techniques like machine learning. So let's talk a little bit more about machine learning and how we can use it in condition monitoring, how we can use it in fault detection to feed into our maintenance workflow. So let's start with the broad field of AI, artificial intelligence. Artificial intelligence is simply a broad domain referring to systems and procedures for making smart decisions. So this can be implemented in many different ways with complex tables or lots of data or decision trees. But when we talk about AI, we're just talking about systems that are able to make intelligent decisions for us. When we talk about machine learning, we're looking at a subset of artificial intelligence. And machine learning is specifically referring to algorithms that use data to build models. So one of the reasons we have seen in recent years, really the last 10, 15 years or so, an explosion in the use of machine learning is that we've seen an explosion in the availability of data. So as time goes on, the sizes of our data sets are increasing exponentially. Our ability to store this data and to process it is increasing exponentially. So our ability to gather information and build meaningful models has skyrocketed in recent years, which has caused this explosion in machine learning. So we can use machine learning, which is essentially using data to build models to drive our decision making. So when we're looking at machine learning and implementing it, there are a lot of different ways that we can approach it. but in all instances, we're basically looking at building a data-driven model. So we have to build a model in some way, and we have to collect data, and it has to be meaningful data, and then we have to choose the right model and then build it. So machine learning typically involves, and to simplify quite a bit, two main phases, a training phase and a deployment phase. So when we're talking about training, we're talking about actually building the model. And this is something that we do offline. So what will happen is we'll take inputs, which we call features in machine learning language, and those inputs get fed into a model. And then the model itself is going to give outputs, and those outputs are predictions. But then what we do in the training phase is we can also feed it a target output. So if, for instance, we had a set of data where we had inputs and we knew what the outputs of the system were supposed to be, we could feed those into our training approach and use some learning rules to constantly correct our model and to build it and to improve it. So this is something that's typically done offline, or that's being done on software that's basically doing this kind of behind the scenes, crunching numbers, adjusting parameters in a model to build it and to improve the outputs and the predictions of it. And then once the model has been built, then in deployment, it's fairly straightforward. We can just deploy that model, take new data, feed it into the learned model, and then the output is going to be predictions that we can use to drive our decision-making process. So in machine learning, there are many, many different models that we can use, and the rules for learning are going to be different. And we're not going to do a deep dive into different model types and whatnot. That's beyond the scope of this discussion. But in general, it's helpful to keep in mind that there are three sort of high-level classes of machine learning techniques that we might be interested in. The first one is what we call supervised learning. And in supervised learning, what we're doing is we're using what we call labeled target data. So that target data, remember, is the output of the algorithm. In unsupervised learning, if we don't have access to labeled data, we don't know what the output is supposed to be, we're kind of taking a blind approach. That's why we call it unsupervised. We can use this approach. In reinforcement learning, we're basically looking to find outcomes that we would believe to be optimal, and then rewarding good outcomes and punishing bad outcomes to tune that model to start making good decisions. So examples, supervised learning, say we wanted to train a model to detect pictures of animals. We could take our model and expose it to pictures of dogs and cats. And we know what the picture of the dog is, we know what the picture of the cat is, so we can label it, and the target output is the label of either dog or cat. The data that we're feeding it are the actual pixels from the image. So we can feed that into the system, show it lots and lots of pictures of dogs and cats, and tell it this is a dog, this is a cat. Over time, after being exposed to millions of images of dogs and cats, it's going to be getting pretty good. And then when we send that into deployment, it should be able to detect with a good degree of accuracy what a picture of a dog is and what a picture of a cat is. In unsupervised learning, we don't have access to that labeled data. We have access to a lot of data, but we don't necessarily know what the output is. So say, for instance, if we had medical data on people, height, weight, blood pressure, et cetera, and we wanted to predict health, but we didn't have any past history that said, well, a healthy person has these height and weight characteristics or these blood pressure characteristics. And so we don't know what that actually looks like. We could use an approach called unsupervised learning, in which it's going to look to group together common characteristics, and it's going to look to determine what a normal state might be and what an abnormal state might be. So that's an approach where we could potentially use unsupervised learning. Reinforcement learning, we've all seen more examples in the news lately of self-driving cars. So a self-driving car might do something like reinforcement learning, where we're telling the car that it needs to get to a final destination, and it's going to try to figure out how to get there. And when we're training it, we're going to reward good decisions and we're going to punish bad decisions, and it's going to learn over time. And then once we feel confident that it's learned sufficiently how to navigate various pathways and get from point A to point B, then we can deploy this model and actually use it. So what about these different approaches and how can they potentially be used in condition monitoring? So supervised learning, remember we said that supervised learning requires large data sets of labeled target data. So what this means is if we had access to an extremely large database of all motors and makes and models, and we knew exactly what it looked like when they were healthy, and we knew exactly what it looked like when they failed, we could perform supervised learning. But that would require a very extensive data set, access probably to OEM information, and to develop a consolidated, comprehensive database would be very difficult and very challenging to approach. Reinforcement learning, typically something like that's not going to apply in condition monitoring because we aren't concerned with how we get to a certain path or to a certain destination via a certain path. We just want to make accurate estimations. This is why, therefore, in condition monitoring, unsupervised learning actually lends itself as a very good approach, because what we can essentially do is look at each machine as an independent entity, and we can monitor an assumed healthy state over a period of time and build a model that is representative of that healthy state. And then when we deploy it and we start to see a deviation from that healthy state, we can send an alert. And this is essentially a technique that you've probably seen when you use, for instance, a credit card. If you have certain spending behavior, or you typically use it at certain locations or certain geographic regions, the credit card company is going to build a model of what they consider normal spending behavior for you to be. But then if you take an unexpected trip overseas and you don't tell your credit card company, you might get an alert via email or on your cell phone saying, hey, did you make this purchase? This looks like unnatural or non-normal behavior for you. And that's what we call anomaly detection. So we can use very similar approaches in condition monitoring, since we're going out into a factory and we're installing on many different models of machinery, many different types of machinery and different locations installed in different ways, a lot of different variables at play. But by using unsupervised learning, we can do on a case-by-case basis, try to understand what normal is for a specific piece of machinery and then look at deviations from that. So historically, in condition monitoring, what the approach that we've used is the intersection of dynamics and vibration with signal processing. So this is a lot of what we talked about in session 2, where we talked about the physics of a mechanical system, and then we talked about the data that was being collected and how we can look at the dynamics of the system and the way that we're processing the data in a way to extract the most useful information. So when we add machine learning to the mix, we're not replacing the dynamics understanding, the physics understanding, or the signal processing understanding, but rather we are supplementing it. So we're leveraging our domain expertise of the physical system, we're leveraging advanced signal processing, and then we're also applying machine learning to it to make even better decisions. So the workflow in terms of system to data to assessment, it starts with the dynamics, it starts with the physical system. So the strategy for condition monitoring solutions is always to start with a good understanding of machine rotation, dynamics, vibration, the physics of the system itself, and then using that to drive the way that the data is processed, using that to drive the way that the data is calculated on the sensor itself, and then sending that data to the cloud to perform machine learning, where models can be trained and deployed so that fault detection solutions can be applied. So let's take a look at what a learned model might actually look like. So in the case here, you can see on the x-axis of this plot, we have RMS values, and on the y-axis, we have peak-to-peak values. So what we've done is we've collected data over time, typically a several-week period, in which we've established what we consider normal operating behavior for this piece of machinery. And you can see the machine learning algorithm learned what we see in blue. That's labeled as the training set. So this is the learning period where all of the data collected from the machine was grouped into these two clusters that are essentially two different operating states. So maybe this machine could be running at two different speeds or two different loads, but you're going to see kind of this grouping of data points that's representative of various normal operating modes of that piece of machinery. And then all of that data is collected by a cloud algorithm and automatically trains, automatically learns based on what has been programmed and designed by the engineers. And then after that learning period is complete, such a system would automatically go into deployment, and it would look for a deviation from what it considers to be normal. So remember, this is that unsupervised learning where it's learning a normal state and it's looking for anomalies from it. So when it starts to see data deviate from it, it flags it and says, hey, this data looks a little bit different. And then it wants to look and see that a substantial amount of data has been accumulated over time, because we don't want to send an alert if there's some sort of intermittent or adjacent vibration next to a motor. We want to be convinced that the machine's behavior has truly changed over time, and we're convinced that there's been a change in state, and that's when we send an alert. So we see that in order to build confidence in making this decision, the algorithm on its own is deciding that a significant number of data points have fallen outside of that baseline model, and then it's going to send an alert. So let's revisit the maintenance workflow that we talked about in session 1. We said that condition monitoring sensors collect vibration data and then send that data to the cloud, where it is then analyzed. Then this is the point in the cloud where we might see a crossing of that velocity RMS level, or we might see the machine learning algorithm detect some sort of anomaly, and that's when it's going to send an alert. So that's what we see as the first part of this workflow. So if that change is detected, then it sends an alert, possibly via text message or email. And then this is where we get to the next step, where now, rather than using that edge process data, we want to collect raw data. If the wireless sensor supports it, we can stream that raw data from the wireless sensor. Otherwise, oftentimes a handheld instrument will be used in a visit to that piece of machinery specifically. And then that raw data can be used to perform advanced analytics. In session 2, we talked about a fast Fourier transform to detect certain frequency components that we can use to relate to various fault types. And then, of course, once we get that diagnosis or that understanding of what's going on with that piece of machinery, then specific maintenance can be performed based on the known or predicted state of that piece of machinery. So I mentioned before that for the edge metrics, we might typically use the low energy advertisements. However, we can do, oftentimes depending on the system, a pairing that is temporary between the sensor and the gateway, where raw data is actually being streamed through completely unprocessed, and then it's going to go to the cloud where more advanced analytics can be used. So this is the point in that workflow where after that initial alert has been sent on that edge process data, then we can take a deeper dive by streaming the raw data and processing it further in the cloud. And we can use different software packages. There are many available out there, and it's beyond the scope of this discussion to dig into all of them. But there are a lot of third-party tools. There are a lot of solution providers who provide this type of analytic solution. All that being said, we can take a deeper dive doing frequency domain analysis or advanced processing techniques and look at the signal and detect, okay, is it an imbalance? Is it looseness? Is it misalignment? Is it a bearing fault, etc. So I'd like to wrap up by talking about a few practical considerations with condition monitoring solutions. So we've talked about some of the technology, some of the data, how it can be used in the workflow, but implementing the solution itself can sometimes be challenging. So I just want to cover a couple of practical considerations. So the first category, price versus value. We talked about piezoelectric versus MEMS, and then taking that solution though and implementing it into your actual maintenance workflow, you oftentimes need to know ROI to make a good decision ahead of time. However, it's not always straightforward to determine. So knowing the cost of unplanned downtime, or at least being able to estimate it, can be a huge step in moving in the right direction of understanding the value of a specific condition monitoring solution for maintenance practice. Another thing that is very common is oftentimes when evaluating condition monitoring solutions, they get limited to a small scope of machinery. And sometimes this can also limit the ability to really understand the ROI and understand the value. So what we're seeing more of in practice now is larger scale pilots that can help answer these questions much faster. So rather than just getting a couple vibration sensors and putting them on 4 machines, well, we don't know if these 4 machines are going to break down or behave abnormally anytime for the next 3 months or 6 months or a year. However, if we look at an entire production line and outfit maybe 50 or 100 assets, then we can start to get a much better idea much quicker on what the true value is and how can it improve decision making. So implementing larger scale pilots can oftentimes be very helpful, and this becomes much more cost effective now with lower cost condition monitoring solutions on the market. Being able to install on 50 assets or 100 assets is now cheaper than ever. And then also looking at buying a product or a full solution versus a service, because there are lots of companies that sell condition monitoring solutions. There are lots of companies that sell pieces of it, and then also companies that sell services. So you can always take the approach of piecing together a solution, buying different sensors and data acquisition systems and software packages. This can be really good if you have the internal expertise and you know exactly what you want to do or exactly what you need to do. But if you don't have that internal expertise, oftentimes buying a turnkey solution that includes the end-to-end, the hardware, the analytics, the data storage, the user interface, the alerting, the machine learning, all in one, that can oftentimes be a very powerful solution to implement. And then there are also lots and lots of third-party service providers, maintenance and reliability service providers, who will use some of these pieced together solutions, use some other available turnkey solutions, combine it with their own services and software packages, and offer really powerful maintenance and reliability services. So depending on what your current maintenance strategy is, there are different approaches that you can take with hardware analytics and various solution and service providers. We talked in the first session about replacing versus supplementing, and there are cases where if no maintenance practice is really used at all, if you're doing run to failure, then anything new that comes in is going to replace maybe a poor practice of the past. So you're adding something that is missing. However, in most cases, there typically are going to be some sort of practices in place, and condition monitoring solutions should be viewed as improving those existing practices, not necessarily replacing them altogether. Another powerful thing that can be used is integration of condition monitoring solutions into existing systems that are already being used. So when you start to get the merging of additional data streams, like say in IoT platforms, where you're pulling in the vibration and temperature data from one condition monitoring solution, but maybe also looking at PLC data or pressure data or speed or performance data, and integrating that in together from multiple sensors, that can be a very powerful enabler in making improved decisions. Also, integrating condition monitoring solutions into CMMS or ERP systems, as long as those condition monitoring solutions have that interface, maybe via an API, then that sort of integration can take place and really add a lot of power to the maintenance practices. And then also, it's a good idea to consider near-term maintenance and inspections versus long-term operations. So obviously, to whoever is running the day-to-day of a factory, that real-time alerting, that real-time analytics can substantially improve day-to-day inspections and maintenance decision-making. This is very important for whoever is managing the maintenance or managing the operations. This can substantially make their lives easier in reducing a lot of those additional costs that are associated with maybe poor maintenance practices. It's also good to keep in mind, though, that even with the added benefit of the day-to-day and the real-time alerting, by collecting historical data over time across multiple machines, multiple production lines, locations within one facility, or even different plants across various geographic regions, you can substantially improve long-term operations decisions. What types of machinery you're using, what types of machinery you're purchasing, how you're deploying it and running it. So the added benefits of a wireless condition monitoring system go beyond just the day-to-day real-time decision-making, but also help essentially to digitalize a factory and get visibility across an entire fleet, which can span many geographic regions. So in conclusion, a proper condition monitoring solution is going to enable predictive maintenance or a condition-based maintenance strategy. And it should be combined with other sources of information. A condition monitoring solution is the key enabler to that predictive maintenance strategy, but it doesn't necessarily replace everything that you've done up to that point. So it's good to combine it with other sources of information if those sources are available. And if it's done properly, it's going to improve inspections and maintenance practices. It's going to improve those high-level operations decisions as well. And at the end of the day, what you're most interested in, of course, is saving money and making your entire operations of maintenance and inspections, et cetera, much easier and much more cost effective. And then finally, new trends in low-cost wireless condition monitoring are now, as we're seeing, expanding predictive maintenance to the entire fleet. So whereas oftentimes in the past, condition monitorings have been cost prohibitive and therefore only being restricted to a certain class of machines, now with newer trends in low-cost wireless remote monitoring, we're able to see entire factories get blanketed with some level of visibility. So that concludes session 3. Thank you. I appreciate your time and walking through this with me, and I wish you the best of luck in your maintenance practices in the future.
Well, thanks so much, Brad. I think we're really happy that by means of your 3 presentations, attendees can get a good overview of both the theory and practice of condition monitoring and some other emerging maintenance practices. So I congratulate you on 3 really great presentations and thank you for them.
Thank you, Kevin. Appreciate it.
We look forward to seeing you in the live Q&A session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided suited your purposes.